The National Electrical Code Handbook publishes wire tables that include metric values. The latest edition of this handbook is the 2020 edition. The National Electrical Code itself, however, does not currently include metric values within its official code text. There's been discussion regarding whether the National Electrical Code should incorporate metric units. There are several arguments in favor of including metric values in the National Electrical Code, and also arguments against it. Arguments for including metric values in the National Electrical Code. Firstly, it promotes international standardization aligning with other global electrical codes. Secondly, it simplifies calculations and eliminates the need for conversions between imperial and metric units. Thirdly, using metric values may improve accuracy and reduce errors that might arise from misinterpretations of imperial units. Arguments against including metric values in the National Electrical Code. Firstly, the existing electrical infrastructure and many installed devices are based on imperial units. Secondly, the process of metrication could potentially be disruptive and costly for businesses and electricians who are already accustomed to working with imperial units. Thirdly, some electrical values are commonly expressed and understood in imperial units, such as voltage levels like 120 volts or 240 volts, and frequency like 60 Hz. At the present time, the National Electrical Code does not include metric values in its official code text. The inclusion of metric values is an ongoing topic of discussion within the electrical industry. It is possible that metric values may be considered in future revisions of the code. When working with electrical codes and standards, it's important to consult the most up-to-date versions and any local amendments that might be in effect. Changes and updates are frequently made to address new technologies, safety concerns, and evolving industry practices. For example, consider a scenario where an electrician is installing conductors in a conduit. The electrician needs to determine the appropriate size of the conduit based on the number and size of the conductors. The National Electrical Code provides tables that specify the maximum number of conductors allowed in different sizes of conduit. These tables are based on the cross-sectional area of the conductors. If the conductor sizes are given in metric units, the electrician would need to convert them to imperial units in order to use the tables in the National Electrical Code. This conversion process can introduce errors and increase the time required to complete the installation. The inclusion of metric values in the National Electrical Code would eliminate the need for these conversions and simplify the installation process. However, it would also require electricians to learn a new system of measurement and could potentially lead to confusion and errors if they are not properly trained. The decision of whether or not to include metric values in the National Electrical Code is a complex one with both advantages and disadvantages. It is important to consider all of these factors before making a decision. The National Electrical Code is a comprehensive set of standards that governs the safe installation of electrical wiring and equipment. It is updated every 3 years to reflect changes in technology and industry practices. The National Electrical Code covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It is essential for electricians, engineers, and other professionals working in the electrical industry to be familiar with the National Electrical Code. In addition to the National Electrical Code, there are also a number of other standards and regulations that govern electrical installations. These include state and local codes, as well as standards developed by organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA. It is important to comply with all applicable codes and standards when installing electrical wiring and equipment. Failure to do so can result in serious injury or property damage. One of the most important aspects of electrical safety is proper grounding. Grounding provides a path for fault current to flow back to the source, which helps to protect people from electric shock. The National Electrical Code specifies the requirements for grounding electrical systems. It is important to follow these requirements carefully to ensure that the system is properly grounded. Overcurrent protection is another essential aspect of electrical safety. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical wiring and equipment from damage caused by excessive current flow. The National Electrical Code specifies the requirements for overcurrent protection. It is important to select and install overcurrent protection devices that are properly sized for the circuit they are protecting. Wiring methods are also covered in the National Electrical Code. The code specifies the types of wiring that are permitted for different applications. It is important to use the correct type of wiring for the application to ensure that the installation is safe and reliable. Equipment installation is another important topic covered in the National Electrical Code. The code specifies the requirements for installing various types of electrical equipment, such as lighting fixtures, appliances, and motors. It is important to follow these requirements carefully to ensure that the equipment is installed safely and correctly. The National Electrical Code is a complex and comprehensive document. It is essential for electricians, engineers, and other professionals working in the electrical industry to be familiar with the code. By following the National Electrical Code, it is possible to ensure that electrical installations are safe and reliable. Regarding wire sizes and ampacity, the National Electrical Code specifies the allowable ampacities of different sizes of conductors. Ampacity is the maximum amount of current that a conductor can carry safely without overheating. The National Electrical Code tables that provide ampacity values are based on the type of conductor, the insulation temperature rating, and the installation conditions. It is important to select conductors with an ampacity that is sufficient for the load they will be carrying. Undersized conductors can overheat and cause a fire. The National Electrical Code also specifies the requirements for conductor dating. Conductor dating is the process of reducing the ampacity of a conductor when it is installed in certain conditions. For example, conductors installed in conduit or in close proximity to other conductors must be derated to account for the increased heat buildup. The National Electrical Code provides tables and formulas for calculating conductor dating factors. It is important to properly derate conductors to ensure that they do not overheat. When working with electrical systems, it is important to always follow safe work practices. These practices include wearing appropriate personal protective equipment, such as gloves and safety glasses. It is also important to energize circuits before working on them. Always use a voltage tester to verify that a circuit is de-energized before touching any wires or components. Never work on electrical systems when you are tired or under the influence of drugs or alcohol. If you are not qualified to perform electrical work, do not attempt to do so. Hire a qualified electrician to perform any electrical work that you are not comfortable with. The National Electrical Code is a valuable resource for ensuring electrical safety. By following the National Electrical Code and safe work practices, it is possible to prevent electrical accidents and injuries. Understanding the debate around metrication involves several aspects of electrical engineering and standardization. Firstly, the basic principles of electrical units. Electrical units are based on the International System of Units, or C, which is a metric system. The base units of the C system that are relevant to electrical engineering are the ampere for electric current, the volt for electric potential, the ohm for electrical resistance, the watt for power, and the farad for capacitance, the Henry for inductance, and the Siemens for conductance. All of these units can be expressed in terms of base C units such as meters, kilograms, seconds, and amperes. Secondly, the practical implications of using metric versus imperial units. In countries that use the metric system, electrical calculations and design are typically performed using metric units. This simplifies the process and reduces the risk of errors. In countries that use the imperial system, electrical calculations and design are often performed using a mix of metric and imperial units. This can make the process more complex and increase the risk of errors. Thirdly, standardization and international compatibility. The use of metric units in electrical engineering promotes standardization and international compatibility. This makes it easier for engineers and technicians from different countries to communicate and collaborate. It also simplifies the process of importing and exporting electrical equipment. Fourthly, the transition to the metric system. The transition to the metric system can be a complex and costly process. It requires retraining of personnel, updating of equipment, and revision of standards and codes. However, the long-term benefits of using the metric system, such as increased efficiency, reduced errors, and improved international compatibility, can outweigh the costs. Fifthly, specific examples of metric units in electrical engineering. Some examples of metric units commonly used in electrical engineering include millimeters for wire diameter, square millimeters for conductor cross-sectional area, meters per second for speed of light, hertz for frequency, and joules for energy. Sixthly, conductor sizing. Conductor sizing is based on ampacity, which is the maximum current a conductor can carry continuously without exceeding its temperature rating. The National Electrical Code tables provide ampacity values for different conductor sizes and insulation types. These tables are based on extensive testing and calculations to ensure that conductors are operated within their safe temperature limits. The ampacity of a conductor is affected by several factors, including the ambient temperature, the number of conductors in a raceway, and the type of insulation. The National Electrical Code provides directing factors to account for these effects. Seventhly, conduit fill. Conduit fill is the percentage of the cross-sectional area of a conduit that is occupied by conductors. The National Electrical Code limits the conduit fill to prevent overheating and to allow for easy installation and removal of conductors. The allowable conduit fill depends on the number of conductors in the conduit and the type of conduit. Eighthly, voltage drop. Voltage drop is the decrease in voltage along a conductor due to the resistance of the conductor. The National Electrical Code recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Excessive voltage drop can cause equipment to malfunction and can reduce the efficiency of the electrical system. Ninthly, short-circuit current calculations. Short-circuit current calculations are used to determine the maximum current that can flow in a circuit during a short-circuit fault. These calculations are essential for selecting overcurrent protection devices that can safely interrupt the fault current. The National Electrical Code provides methods for calculating short-circuit currents. Tenthly, grounding and bonding. Grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to flow back to the source, which helps to protect people from electric shock. Bonding connects all metal parts of the electrical system together to create a low impedance path for fault current. The National Electrical Code specifies the requirements for grounding and bonding electrical systems. 11thly, motor calculations. Motor calculations are used to determine the size of conductors, overcurrent protection devices, and disconnecting means for motors. The National Electrical Code provides methods for calculating motor currents and for selecting the appropriate components for motor circuits. 12thly, transformer calculations. Transformer calculations are used to determine the voltage, current, and power ratings of transformers. The National Electrical Code provides methods for calculating transformer parameters and for selecting the appropriate transformers for different applications. 13thly, lighting calculations. Lighting calculations are used to determine the number and type of lighting fixtures needed to provide adequate illumination for a space. Lighting calculations take into account the size of the space, the reflectance of the surfaces, and the desired illuminance level. 14thly, renewable energy systems. Renewable energy systems, such as solar photovoltaic and wind power systems, are becoming increasingly common. The National Electrical Code provides requirements for the installation of renewable energy systems to ensure that they are safe and reliable. The National Electrical Code is a living document that is constantly being updated to reflect changes in technology and industry practices. It is important for electricians, engineers, and other professionals working in the electrical industry to stay up to date on the latest requirements of the National Electrical Code. The inclusion of metric values in the National Electrical Code would have a significant impact on the electrical industry. It would require a significant investment in retraining and equipment upgrades. However, it would also offer several benefits, such as increased efficiency, reduced errors, and improved international compatibility. The decision of whether or not to include metric values in the National Electrical Code is a complex one that must be carefully considered. The National Electrical Code, or NEC, serves as the benchmark for safe electrical design, installation, and inspection to protect people and property from electrical hazards. It is developed by the National Fire Protection Association, or NFPA, and is updated every 3 years through a consensus-based process involving experts from various fields including electrical contractors, engineers, inspectors, and manufacturers. The NEC covers a wide range of electrical topics including wiring methods, overcurrent protection, grounding, and equipment installation. Its primary goal is to minimize the risk of electrical shock, fire, and other hazards. Compliance with the NEC is often mandated by state and local laws, making it a critical standard for electrical work in the United States. The NEC is organized into chapters, articles, and sections. Each section provides specific requirements for different aspects of electrical installations. For example, Article 250 covers grounding and bonding, while Article 310 deals with conductors for general wiring. Understanding the structure and content of the NEC is essential for anyone involved in electrical work. The NEC provides tables that specify the allowable ampacities of conductors. These tables are based on the conductor's size, insulation type, and installation conditions. For example, Table 310.16 lists the ampacities for conductors rated 60 degrees Celsius, 75 degrees Celsius, and 90 degrees Celsius based on the ambient temperature. These ampacity values are crucial for selecting the right conductor size to prevent overheating and potential fire hazards. Overcurrent protection is another vital aspect of electrical safety. The NEC requires that all electrical circuits be protected by overcurrent devices, such as circuit breakers or fuses. These devices are designed to interrupt the flow of current in the event of an overload or short circuit, preventing damage to equipment and reducing the risk of fire. The NEC specifies the maximum allowable overcurrent protection for different types of circuits and equipment. Grounding and bonding are essential for minimizing the risk of electrical shock. Grounding provides a path for fault current to flow back to the source, causing the overcurrent device to trip and energize the circuit. Bonding connects all metal parts of the electrical system to create a lower impedance path for fault current. The NEC provides detailed requirements for grounding and bonding electrical systems to ensure safety. The NEC also covers wiring methods, which specify how conductors are installed and protected. Common wiring methods include rigid metal conduit, electrical metallic tubing, or IMT, non-metallic conduit, and cable wiring. Each wiring method has its own set of requirements regarding installation, support, and protection. The NEC specifies which wiring methods are suitable for different applications and environments. Equipment installation is another important area covered by the NEC. The code provides requirements for the installation of various types of electrical equipment, such as lighting fixtures, receptacles, switches, and appliances. These requirements are designed to ensure that equipment is installed safely and correctly, minimizing the risk of electrical hazards. The NEC also addresses specific requirements for hazardous locations. Hazardous locations are areas where flammable gases, vapors, or dust may be present, increasing the risk of fire or explosion. The NEC classifies hazardous locations into different classes and divisions, each with its own set of requirements for electrical equipment and wiring. The NEC is not intended to be a design manual, but it provides essential information for designing safe electrical systems. Electrical engineers and designers use the NEC as a guide to ensure that their designs meet the minimum safety requirements. However, it is important to note that the NEC is not a substitute for sound engineering judgment and experience. The NEC is constantly evolving to keep pace with technological advancements and changing industry practices. The NEC revision cycle occurs every 3 years, with each new edition incorporating updates and revisions based on input from industry experts. Staying current with the latest edition of the NEC is essential for anyone involved in electrical work. The NEC is a complex and comprehensive document, but it is essential for ensuring electrical safety. By understanding and following the requirements of the NEC, electrical professionals can help to protect people and property from the hazards of electricity. It is a critical resource for designing, installing, and inspecting electrical systems. The NEC is a valuable tool for promoting electrical safety and preventing electrical accidents. It is important for anyone working with electricity to be familiar with the NEC and to follow its requirements carefully. The NEC is a key component of a comprehensive electrical safety program. It works in conjunction with other safety measures such as training, personal protective equipment, and safe work practices to minimize the risk of electrical hazards. The NEC is not just a set of rules, it is a framework for creating a safer and reliable electrical environment. By adhering to its principles, electrical professionals can contribute to a safer world for everyone.